So back in February, basically, I wrote a Decompiler because everybody was talking about Ethereum. I wish I'd bought coins instead. I would have made more money out of it. So just to give you a quick introduction, if you don't follow me already on Twitter, so this is my handle. I'm also the organizer of a conference in Dubai. I didn't come to Vegas since 2011. I took a Vegas break. No, it's okay. I'm fine coming back again. And my new claim to fame is to have been called a fun guy by the shadow brokers. So, so just so you know, I won't be talking about like what blockchain is, Merkle trees, and all those things. And so we're going to focus on smart contracts, how to decompile them as Windows reverse engineering. I thought it was interesting to analyze like the VM itself. And I'm also releasing a tool which is going to be open source, so I'm going to give the link at the end. And yeah, and of course like the tool is not perfect, so you're more than welcome to contribute and to give like a pull request. Just like a short overview of what we're going to be talking about today. We're going to be talking about the EVM, its memory management, how we can do like type discovery, which is important, especially with mainly like static analysis, but also if you're building a decompiler, obviously, how it can be used for like static and dynamic analysis, and the non-type of class of bugs that we know so far, and what to expect in the future. So, how many of you are familiar with Solidity? Please raise your hand. So, basically, like Solidity is the compiler for Ethereum. So, the way Ethereum works is like to execute those smart contracts is basically like a software layer on top of the blockchain. So they use a compiler called Solidity, which is translating code, which is written in a JavaScript-like format into bytecode. And Porosity is the tool I'm going to be describing today and releasing. So if you're familiar with like chemistry and physics, it's the exact opposite of Solidity, hence the name. So far, like there is a lot of accounts on Ethereum. There's like millions of them, and if you look at the actual number of contract accounts, it's almost 1 million. Probably it's 1 million by now. But the actual number of verified contract is very small, and the definition of what's a verified contract is very obscure. But basically, it comes down to if the source code is provided. So when it comes down to reverse engineering, like usually don't care if you have the source or not, but it's interesting that since this software layer had been introduced with Ethereum, we see like a need for reverse engineering. And especially since Ethereum introduced that concept of ICO to leverage use cases for smart contracts, we have heard a lot of stories since the beginning of the month. I think here I'm mentioning like but I think like 3 different stories happened this month, including one with CoinDash, which is like the first one. Someone changed like the address where to receive the funds. And most recently, Parity, which is a project started by one of the key developers of Ethereum, had a vulnerability in one of their smart contracts, and 30 million got lost. And few days back, something happened with another ICO and 10 millions vanished. So that's basically what happened when you're like writing software to store money but don't have proper like security checks. It's more damaging than a blue screen of death. It's like a wallet of death. But so the EVM, so the Ethereum virtual machine, so for like each, like you have like 3 concepts, like account, contract on blockchain, and pretty much like interchangeable. Even like personally to me, like the difference is like quite obscure, but I'm mainly like focused on the actual bytecode, which is stored on the actual blockchain. So a smart contract is basically a synonym, a more fancy word for bytecode, and it's stored inside the blockchain. It uses 160 bits addresses, and addresses correspond to an account. And one of the specificity also of the Ethereum virtual machine is that it uses like 256 bits registers. But they don't really have like registers like you would know in traditional infrastructures, like with x86, for instance. So they have like this concept of virtual stack. The more you look at it, the more you see like it was kind of like they're trying out different things. It's still like the outcome is still pretty good, but if you're gonna build like a virtual machine, a lot of the things are a bit shaky. So for those who are not familiar with Solidity, that's basically what it looks like. So on the left, that's a simple like coin contract. So it's very simple. Usually you have like few routines, you have like some storage memory, and even like the instructions themselves are like quite straightforward. You do like many like you store like an integer. You do subtraction, addition, and that's pretty much it. So like the level of complexity of a contract is very far away from the complexity of a kernel driver per se. Then you compile it using Solidity, and then you get like all that bytecode, which is gonna end up on the actual blockchain. And at the same time you compile, it also saves the interface, which is going to be used for like other like smart contracts to call that specific contract. So regarding the memory management, so you would have like 3 different types of memory that are like significant. So the first one is the stack that I was mentioning before. Like under traditional architecture, you would use like the stack to push arguments, at least with x86, not with 64-bit architectures. You would use like the stack to push arguments to a function. So here, you push arguments to opcodes. And then there is like a limited size to the actual stack, which is 1024 elements. And then you would have like 2 types of storage, so a persistent one, which is designed, as its name says, like to retain data, and another one, which is like more volatile, that you can identify easily from the instructions. So the volatile one is interesting because that's basically what will be used to like store strings. But even if you look at it, the way it's done is still a bit dirty, but it does the job. Like I was saying, like smart contracts are like very simple, very simple per design. So if you do like static or dynamic analysis, control flow graph, and especially if you write a decompiler, one of the most important things to understand is the actual like control flow of your program. So the first thing we need to know is basically how to identify basic blocks. So at least in that case, with smart contract, it's so much easier than a traditional architecture. Because there's not all those concept of like code obfuscation and everything don't really exist yet with smart contracts. For sure, we would like expect them in the future, but it's not like present yet. So in most of cases, they have like this instruction called jump test, which is indicating like the beginning of a new block. In most of cases, I would say like 85% of them, you would have this instruction at the beginning of each block, and then you have a bunch of different instructions for like conditional jumps or traditional jumps. The difference with traditional architecture is like on x86, for instance, you would have your opcode and then the destination, right, in the same same opcode. Whereas like here, they first push it on the stack and then execute the opcode for that. But the main difference is sometimes they're just going to push it at the beginning of the function, do a bunch of instructions, so you would totally like forget which was like the destination address. So that's why you would need like to write a pseudo debugger that you would have to emulate most of the instruction to keep track of all the destinations. And that's basically like one of the main limitations of static analysis with smart contracts. Otherwise, like most of it could be like done statically, but because of like those like weird scenarios where like the destination is stored beforehand, you would have to like emulate like certain basic blocks in order to like keep the destination of the basic block. For like stack manipulations, there is basically like a few instructions. So you have like a duplicate, swap, and pop and push. It's pretty straightforward. When it comes to the actual opcodes of the EVM, you can have like different categories. So obviously, like the main one is for like arithmetic functions. It's mainly designed to like deal with money, to create like wallets for transactions, which makes sense, right? And then you have like the block environment and the environmental informations, where you would have information about the sender, the person receiving it, and then you have all the memory related operation, plus some logging operations to keep track of certain events. So, like I was saying before, the main thing here, so that's an example, where basically like opcodes are more like functions because you need to push the arguments on the virtual stack. So here, for an addition, you would push like the two variables that you want to add, and then you would retrieve the argument not in a register, but in the first item of the actual stack. So that would come like that if you would write it in a EVM pseudocode. And then you have like EVM calls. So those ones are like pretty interesting. They allow you to call like a different contract. So you have multiple type of calls. So you have like the regular call, but also like delegate call, which is what had been abused like recently in the parity contract. Which is also interesting from the perspective that basically you call like third-party libraries that you don't necessarily own. So that's also an interesting context. So it leaves a lot of opportunities for like undefined behavior. And when it comes down to like static analysis, dynamic analysis, or even like trying to define your scope, well, that creates a lot of issues. There are like 4 exceptions for like hard-coded contracts, so including for SHA-2, identity function, and for key recovery functions. So like the contract addresses are like 1, 2, 3, and 4. So whenever you look at the actual bytecode, you would notice like those static addresses. So when it comes down to user-defined functions that are exportable by default by each smart contract, you would easily recognize how many parameters they have based on the call data load instruction, which is basically reading the environment information block, which is basically like a buffer that contains all the input parameter, including the hash of the function we want to execute. So the structure of that block is pretty straightforward. Like the first 4 bytes would be the hash method of the actual function, which we're going to describe later. And then it will be followed by the actual arguments. So if you look at the actual like pseudocode here, so basically like A and B are being recovered, and the first parameter is like the actual offset inside that block. And then for the addition, that's what you would get. So that function is like very simple, so it's an addition, right? But that's basically what it would look like in pseudo EVM code. So when it comes down to type discovery, the main type you would see and the main type you want to recognize are addresses. So if this is like the address of the sender, the destination of the wallet, or of another contract, so it will be like encoded on 160 bits, right? And most of the time, every time you need something which is not on 256 bits, right, you would see a hand operation. So in most of cases, you would see like, in some cases, you're going to see it like hard-coded, but in most of cases, you're going to see like some EVM assembly like optimization, like the following one, where it's using like it's computing like the mask dynamically. So there is like few of them that we can recognize like very easily. And again, like if we do like type discovery while emulating the code, we would actually we would even be actually able to just like check the mask associated to the instruction. So now that we have seen how like the actual EVM is kind of working, let's talk about the bytecode now. So you're gonna have like two different categories. So you're gonna have like the preloader code, and which is gonna be in charge of copying the actual smart contract, where like all the interesting stuff is inside the executable memory, and then which is basically like the runtime code of the contract, and then so the runtime code, which is basically what we want to analyze, contains all the information that we want to spend the time on. So it would contain the whole class, the whole contract, so each function, and which is basically like the what had been like produced by the Solidity compiler. So this is what the actual like preloader looks like. So there is an instruction called code copy, which is basically in charge of like taking the actual bytecode of the contracts that we need to put it inside the executable memory, so we can execute it after at the offset 0. And once we enter inside the actual smart contract, there is like a dispatcher which is in charge of splitting all the different functions. So the way it works is basically like a giant Suiche instruction. So it would first like recover the hash method from the call data load instruction, and from that, so here you can see even like the code optimization, where basically it's just first reading like a 256-bit register, and then from that it would like apply a mask to only extract like the first 4 bytes. So that's basically like the hash method. And then you enter in a switch statement, which on each switch statement is corresponding to an actual function. And in some cases, you're going to also have a fallback function. So for each, so if there is an unknown method which is not recognized by the smart contract, it will just execute a method by default. And in some cases, like in the case of the parity contract, which is what we're going to see after also, it redirects like a call blindly to another contract. Well, that's not the kind of things you would see like your kernel doing, you know? People would start to freak out, to be honest. But that's something that seems normal for people writing smart contract. Some of those things, to be honest, are still obscure. Like, I don't really understand why you would have a fallback function. So, I mean, I understand why they did it, because like this thing where they want contracts to be like backward compatible and forward compatible. But the source of so much problem, like by design, if you think of security, does not make much sense, to be honest. So function hashes, the way they're like computed, basically they just take like the function name and the parameter of each argument, and they just like stick them together and compute like the share-free of that input. And the result of the first 4 bytes would basically be the hash method. So it's pretty straightforward. So if you have like the ABI, so the actual interface of the contract, you can easily like recompute it. But if you don't, from the actual like switch function, you can just like extract the actual like hash method from the runtime code, and you can create like a name on the fly, like you would do like with IDA, where you just give like a sub-function with the actual offset of the function when you don't have symbols. So like the ABI JSON file is like the equivalent of symbols for smart contracts. So here that's like the instruction I was mentioning, where they basically extract the 4 bytes. And then that's like the pseudocode for it. So here is like a comparison if you purely do like static control flow, like reconstruction, or if you try to emulate, so as you can see in some cases, you really need to emulate the code to keep track of all the actual like destination and pointers. So that would be like a simple contract where you would have like two functions, which is here. So once you can like start to analyze the actual like runtime code from that, like I was saying, it's basically like a giant switch, but we know that each case of the switch is basically a function for it. And then once we decompile it, we would get something closer to what's on the right of the screen. To go a bit more into the detail of the runtime code. So here, for instance, like the double function. So in yellow, we have the actual hash of that function. Then it's going to jump to the offset like 24, which is marked with the jump dest instruction. And then it's pushing the argument 2. Then we're having a new block. So here, in that case, there is like a jump dest, but it's not a new basic block, but it's used by another function. It's a shared basic block. And then you're just going to do like the multiplication. And same thing with the triple. We're going to see it's going to read same thing again, like the input parameter, push like a 3, and then execute like the multiple instruction. So, and if we go back to the initial like source code of it, that's basically what it was doing. It was pretty straightforward. So obviously there are like smart contracts that are way, well, I would not say like way more complex than that, but were like more complex than this. But that's basically to illustrate how easy you can decompile the actual code. If we look at the bug I was mentioning before, so this is the parity bug that happened like a week ago. Remember when I was talking like before, there is like different type of call. You have like a call, a delegate call. They allow you to call like a third-party contract. And then in some cases, you have like a fallback function that allows you to execute a contract, to execute like code if like a method is unknown. So here, like the address in the constructor, like the address was hard-coded, and then you know it's in green, it's computing the actual hash method like dynamically, and delegate call is going to execute that specific function. And then for some random reason, you add like a fallback function that was basically like allowing you to call like any function inside the wallet library and to pass any function or parameter you want. So that's why I was saying like some of concepts are like really obscure. That was basically like the actual reason for the vulnerability. So obviously like now looking at it, it's obvious, but that's a new type of bug that have been discovered by the attacker. That's a pretty good find. But now like once you know that type of bug, it's pretty obvious. So like those fallback functions, so if you have like a switch with executing code with no actual like hash, so that's what your fallback function would be. So I mean, then it's like a design issue, right? So the main reason for that is, well, keep in mind, so it's adding like a software layer to the blockchain, right? But also means that if there's like a security bug in it, well, you cannot patch the blockchain, right? That's the main thing about it. It's like retaining data and moving it around. So the main reason, because from reading about it, it's sort of like backward and forward compatibility because of this lack of capability to apply patches. To be honest, still does not make sense. I think it's stupid, but whatever. That's not how you can design a language which is verifiable, because you have like too many unknowns. If you start calling like third-party libraries, you don't even know what's going to be called. You have to predict all contracts and all future contracts. I mean, like, imagine if your kernel would be doing the actual same thing, you know, like that would be nuts. You would start to see people rioting in the streets, you know. Well, I hope so. So the actual way that bug was fixed is basically like some of the functions were designed to be private function. And so when it was able to call the library again directly, any function, the actual constructor or they could even like recall the actual constructor because it will not even check if it was initialized or not. So those are like the type of bug you would see like with smart contracts. It's very far away from like the classical bugs you would see with like buffer overflow and everything. Here is another example of like vulnerable contract, so that's similar to what the AO was using. So here, like the vulnerability was basically here. It's similar to a REST condition, so basically same thing. It comes down to like a fallback function being reused. So that would create a REST condition where like the balance will not be initialized on time. So for that type of vulnerabilities, the good thing is because there is not many instructions, you can like tag each basic block to see what they're doing. And every time there is a call with an external contract, you will track it either as a warning or as an error. So in that case, we could see that the SS store instruction was being used after, so it would be like easy to analyze. I can show you a quick demo. That's the actual like smart contract itself. So to call the tool, basically you can just like provide the you only need to provide like the actual like bytecode. If you have like the symbols or the ABI JSON file, you can just pass it, and then you just like run the tool to see. And once you like give it as an input to the tool, you can easily reconstruct something very close to the actual source code. So, and if you had like some features, because to build like a decompiler, you basically build everything you need for like dynamic analysis and also static analysis. So you can easily. Oh, I didn't see the subtitles over there. That's cool. Yeah, you can easily like use it to track potential vulnerabilities, just like you would have with most of compilers now. When you have like prefast or prefix with Visual Studio, you have a lot of like static analysis tools that can be used whenever you are writing code, right? So now, like if you look at the actual like smart contract community, they're still like building all those tools. It's something very new. So a lot of the tools that we would find like pretty obvious with GCC or Visual Studio Compiler are not present for those type of software. So because like the whole concept was like to introduce a software layer to it, but it comes without a lot of testing tool, which would be required for enterprise softwares. So far, there are like a few class of bugs that have been detected. So the first one was like the REST condition used for like DAO, then called stack vulnerability. There's some good papers about it, where, like I was saying before, like the virtual stack itself is limited, and once you use all of it, well, it's not even returning an exception. And for a while, there's like some issues with like throwing exceptions. Reverting like the state of a contract. Those were like concepts that are like very new, that have been introduced like recently. Time dependency vulnerability, while some of the actual like instruction give you like some time information, but they're related to a block. So you can easily like guess like the future output, and delegate call would be what happened with the parity contract. So there is a fork of Ethereum called Quorum, created by JP Morgan, which is pretty interesting because the main reason people were a bit worried also with Ethereum is basically if you're an enterprise, you cannot just have everything like written like transparently. So they introduced this privacy layer and permissions to smart contracts, which is pretty cool. Like the Quorum team is here, so I don't know if you guys want to stand up. I don't know if people are gonna see, but that's a pretty cool project. We see a lot of stuff happening around like Ethereum, which is pretty cool. And this week, like Quorum just released a bundle to integrate like Porosity to check like nodes inside the actual network. So that's pretty cool too. And like I was saying, the main thing which is a bit worrying, and what we hear like so many like stories about the ICO's hack, and for sure why we're gonna see more of those stories like over the summer, is mainly because there is no proper like testing tools for that new like software layer, which is pretty nuts, you know. You guys have seen how long it took for like traditional software to get like proper security tools to be tested, even like SDL stuff, like those type of like high-level framework. While with smart contracts, it's pretty much ground zero. I've never heard of it in most of cases. That's why there's like a need for like such tools. So here is like some screenshot of the Quorum and Porosity integration. So then it can be integrated in the actual workflow, which is pretty good, at least to think of integrating tools like that in the actual workflow. It was very fast for the Quorum team to do the integration. They have a pretty good framework, so they can actually like add more and more tools like very quickly, which is pretty good. And in my opinion, it's like a requirement if people are gonna start really using like smart contracts seriously, especially to store money. Again, like if you write a smart contract, most of the time you use it to store money, right? Not to browse YouTube and watch cat videos. I mean, yeah, you know, like if you find like a 0-day in like in a web browser, then you would have to struggle to find where to sell it. Well, if you find a bug in a smart contract, you just like take the bank, you know. It's like being a Lazarus group, but for cryptocurrency. So like I was saying, for sure we would see like more and more testing tools, and like we can definitely expect like by the end of the year even more like issues with like ICO's hack, since like it's like the new thing, everybody wants to like raise money with ICOs. We're getting the tools, so there is like some improvement required for like for a lot of the conditional statements. And when it comes to Ethereum and security, like I was saying, is like there is a fast-growing community, especially like now the main incentive is, well, either you want to steal money or you want to protect your money, right? So it's pretty straightforward in terms of motives if you want to get into like smart contract security. And like I was saying, initially when I looked at it, I was like, oh, why is everybody talking about blockchain? It sounds like really boring. Then I saw there were like some like virtual machine around. I was like, oh, maybe there's some interesting thing to do. And for those who are like familiar with virtual machine vulnerabilities, well, QEMU has a lot of them, but then you have like, you know, like talks like Cloudburst that happened like many years ago. I think it was like at 2010 or something, where basically you would be able to do a VM escape, and now like VM escape are becoming more and more common. Even like Microsoft now with Hyper-V vulnerabilities are raising their bug bounty. Well, you can be sure if you have your own virtual machine, you can also expect bugs in it, right? And then like the whole thing of claiming it's sandbox does not really apply. So the question now is Ethereum going to stay alive, and if their virtual machine is going to be the main virtual machine, or if we're going to see like more provider for smart contracts with their own virtual machines. I was looking at the roadmap for next year, and I saw they are planning to use like WebAssembly. I had no idea what was WebAssembly, and then I looked into it, and basically, so that's so it's being described. It's a portable load time efficiency format. So you have like your own bytecode that can be executed by most of the JavaScript engine, like V8 or SpiderMonkey. And so they're planning to use the same engine that we would see in web browser to a smart contract. I don't know if it's a good or bad idea. I guess from the fact that it's also going to be used by other platforms, it would also benefit of the auditing for that specific language. And in terms of performance, I've seen like some cool stuff. Like if you look at the demos online, the guys are like running like almost like video games with it. They can even like compile, well, I don't know if it's a good thing or not, but you can compile like C++ code into like WebAssembly. I mean, from an attack surface, it seems a bit confusing. You go from like having a VM with a specific set of instructions to like being able to compile C++. So I don't know to which extent it's going to be used in the Ethereum VM by next year, but for sure we would see like stuff leveraging that. So there's some people I wanted to thank who helped me like during the paper. So including like the DEF CON review board, because initially I was just sending a decompiler. I was like, but can we use it for security? I was like, well, obviously it's a decompiler, so you can do anything. So they kind of pushed me to do like the security analysis for it. So if you want to download like the slides and the actual white paper, which is more complete, and in case you didn't understand my French accent, which I can understand, but what can I say? I'm French, I'm not gonna apologize. But you can download like the actual like tool at this address. And yeah, if you have any question, you can either drop me an email, or we have 3 minutes now. So I don't know, it works for like Q&A here. But yeah, if you have any question, let me know.